Alright, so if you have seen the first video on numbering systems, that's great. Welcome to the second video. If not, I encourage you to go back and look at the video on numbering systems before looking at this video. We're going to cover some more advanced topics regarding the binary system in general. In this one, we are going to look at negative numbers in binary, and we are going to look at binary coded systems. So in the technology world, you'd know that computers read and write and do all functions in the form of machine code, formed by the binary numbering system. The binary digits that form a number are called bits. Up until now, we have looked at positive binary numbers, so you're probably wondering how negative binary numbers work. Well, there are several different ways to represent a negative binary number. The easiest way is to simply add a single bit to the left of a number, like so, and represent it as a sign bit. The sign bit will display a 0 if it is positive, or a 1 if it is negative. So for example, a number like I'm showing here is negative because a 1 is in the leftmost bit of this number. If I want to negate a number using this technique, I simply change the sign bit from a 1 to a 0, like so, and it is now a positive number. But binary numbers do not negate this way when it comes to machine code or doing any sort of arithmetic in binary at all. So while it is the easiest technique, it's not the most commonly used, or in this case, I haven't seen it used at all in engineering. There are two techniques, however, to negate binary numbers that are more common, and we're going to look at them now. The first technique is called the ones complement. Before we begin, I'd like to mention that most problems that involve negating numbers with ones complement, or its more commonly used form twos complement, which we will see later, will ask for a specific number of bits in a problem. That is why the first step is extremely crucial when you have to pad the number with zeros on the left side until you have the number of bits you, or the problem that you're doing anyways, want. Then, after that, you invert all the digits. 0 digits become 1, and 1 digits become 0. So let's go back to our first problem, and this time we will negate it using the ones complement. Since I have mentioned that this is a positive binary number, I'm going to go ahead and pad a 0 to the left of this number. Let's say I want 7 bits in this problem. So I will just have to pad 1 0 like so, and then I invert all the bits. So zeros become ones, and ones become zeros. There, and that is the ones complement. The answer is 1011010. Easy enough? Well, a more common technique that is used works almost the exact same way as the ones complement, but with one additional step, that after you invert all the digits, you have to add 1 to the new number. This is what is called the twos complement. So let's go back to our previous problem and do the twos complement of this number. Again, we will follow the same first two steps as we did with the ones complement, like so. And now we will add 1 to the new number. Voila, there it is, the twos complement. The twos complement is the most commonly used of all the techniques and is used mostly in computer code, computer variables, computer languages, and binary arithmetic, which you will see in the fourth video of this series. With both ones and twos complement, if I wish to add more bits to my negative number, all I have to do is pad the number with additional sign bits. In this case, ones, since it is a negative number, right here to the left. This cannot be done with our first technique since it changes the number to something entirely new, but with 2 or more ones in the leftmost end of the number. But with the complement techniques, it's a-okay. Because if we have to negate a number, we're going to be flipping every bit, not just one sign bit. This provides us with one of the advantages of using the ones or twos complement techniques, rather than just simply inverting the leftmost bit. If I wish to negate the number using twos complement, all I have to do is just do the opposite of what I did. Subtract the number by 1, like so, and then we're going to invert every bit. Ones become zeros and zeros become ones. And there we go, we have a positive number. Try doing these 3 problems yourself. We're going to do the bottom 2 problems in about, I'll give it a couple seconds. Pause the video now. The reason I want to take a look at these bottom 2 problems is because how they are represented. In these bottom two problems, we're going to negate 1, 1, 1, 1, 1, which is basically 2 to the 5th minus 1, or 31 using 2's complement. And then we're going to negate 1 using 2's complement. So what we are looking for is negative 31 and negative 1. So let's follow the steps. First, we have to pad the numbers with 0 since they are positive numbers. Of course, we don't have to do it here since I've already done it for you. Next, we are going to invert these bits, like so. Zeros become ones and ones become zeros. And finally, we are now going to add 1 to each of our numbers, like so. If we took out the leftmost 3 bits of each of these numbers, what we would get is basically the exact opposite of each other. This last problem in particular, representing negative 1 as all ones, well, we do know that negative 1 plus 1 equals 0. So what happens if we add 1 to a number that is of all ones? Well, obviously what we get is a 9-digit number, which contains 1 and 8 zeros. But considering an 8-bit binary number, we take out the leftmost bit, leaving us with, yep, all zeros. Intriguing, isn't it? Now, I mentioned in the previous video how you can easily convert from binary to hexadecimal by simply grouping a number of binary bits together and forming a number. This form of grouping binary bits together is also used in a popular form of grouping and converting known as the binary decimal code. Like converting from binary to hexadecimal, a binary coded decimal converts a decimal digit to its corresponding 4-bit binary number. In this case, the minimum digit is 0, which can be coded as 0000, and the maximum is 9, which is 1001. Now, obviously, the numbers 10 through 15 in binary are not used. Just like converting binary to hexadecimal, we code this decimal as if it were a hexadecimal number. Let's take a look at an example here, 67. First, we'll take the first digit here, 6, and we will code it 0110. Next, we are going to take the other digit, 7, and we're going to code it 0111. You will find that if you take an engineering digital design course, especially in the second level of this introductory course, that this type of binary coded decimal is very popular in design problems. Now I'm going to show you a couple other types of coded systems that you might find in your book. Here's one that I found that is fairly common. It's called the exceed 3 decimal, which is basically just the binary coded decimal plus 3. So your minimum digit 0 is 0011, and your maximum digit is 9, which is 1100. If you coded 67 in this one, all you have to do is simply code the 6 first, which is 1001, and then the 7, which is 1010, like so. Finally, I want to end this video with the gray code, which is a numbering coded system that is going to be very popular later on. The gray code is focused on switching only one bit at a time, such as 0000 for 0, and then we switch the 1 bit here, then we switch for 2, we switch the 3rd bit, and so on, as I'm going to show you here. It switches only the leftmost bit that is going to be switched to normal binary counting. If you want to know more about gray code right now, I suggest looking at a Wikipedia article. It is quite interesting stuff. Well, to say the least. Alright, so that's it here. Next, we are going to convert from octal to hexadecimal, and then we're going to just go all out and try to convert with any numbering system. Basically, anything from base 2 to base 36 to base whatever, as long as you have symbols or numbers or letters that you can use to represent digits. So anyways, if you like this video, please thumbs up. I just noticed that you cannot rate a video anymore. I guess the star system has been gone quite a while ago, and I should know that since I frequent YouTube a lot. Stupid me. So please, thumbs up the video, comment, and subscribe, and I will see you next time. Thank you for watching.